Welcome. In this session, we'll explore the vectorization of a matrix and the reshaping of a vector into a matrix. We can treat a matrix, so we'll say a matrix is a vector. And let's underline that, and let's say that we can do this. So this is because it satisfies the axioms of a vector space. So, for example, suppose that we have, suppose we have any matrix A that has m rows and n columns, and any matrix C that also has m rows and n columns. Then for any real number alpha and any real number beta, alpha times A plus beta times C is a matrix with m rows and n columns. So that's one sense in which a matrix is a vector. Another sense, and this is the way that we'll look at here, sense is this is referred to as vectorizing. So we can vectorize a matrix. And what this does is this maps a matrix which has m rows and n columns, and it maps it to a vector that has m times n entries. So this is sometimes called, this is also called unraveling. Unraveling a matrix. So there are two conventions to do this. The convention that we'll use, which is the MATLAB convention, is what we'll do is we'll vectorize by taking the first column and then the second column and so on. So what we'll do is we'll say that for a matrix that has these m rows and n columns, that we can write as, we could write that as A1, A2, and so on until we get to the nth column. We'll define the vectorization of A to be the vector that is, and what we'll do is we'll unravel that first column and we'll start by putting A1 there. Then we'll unravel the second and we'll put A2 here. And we'll continue until we have represented all n columns of the matrix. So that is how we'll vectorize. We'll take a matrix and we'll just copy all of the data into one great big vector. And in MATLAB, the function is called vec. Now, to reverse this, we can say A is the result of the reshape function of A, and, sorry, the reshape of the vector A, and now we have to tell it that it has m rows and n columns. Let's observe immediately that this is not a mathematical inverse, which is why I'm referring to it as a reverse. And the reason is that this vectorization is a many-to-one map. So, for example, if m was 6 and n was 4, then there would be 24 entries. But there are many different ways to factor 24, into two numbers, and so when we're given a vector that has 24 entries, we don't necessarily know the original size and shape of that matrix. We know the number of total entries, but we don't know exactly what its shape is. So let's take an example. So let's say that what we're looking at is, we'll say A is 2, 3, 5, 7, 11, 13, and then let's have a matrix C, which we'll say is 2, 3, 5, 7, 11, 13. So the vectorization of the matrix A will be, we'll write 2, 3, 5, and then we'll write the second column, which is 7, 11, 13. And if we were to vectorize C, it would be 2, 3, 5, 7, 11, 13. So the vectorization of these distinct matrices is the same. So we could reshape. We could reshape the resulting vector as 3, 2, or we could reshape this as a 2, 3, and that would produce A, and that would produce C. And of course, you can see that if you tried to reshape A and it was 6, 1, it would return the same vector as A, and if you did reshape A 1, 6, that would be the one form or the transpose of that vector A.